Hi everyone, we're Team 2 and our project focuses on forecasting shale reservoir potential with carbon dioxide enhanced oil recovery, simulation, and economic modeling. My name is Emma McKay and I'm working with Michael Furrow, Richard Robinson, and Francis Leonard. The United States Energy and Information Administration estimates a 28% increase in world energy consumption by 2040. With the exception of coal, the utilization of all energy sources will increase between now and 2040, especially petroleum. While near-term shale production looks optimistic, the long-term performance of shale reservoirs is highly uncertain. Since conventional reservoirs are being depleted, this calls for innovative, efficient, and economic enhanced oil recovery techniques. Unconventional production is expected to increase to compensate for the decrease in conventional production. Shale's porosity values range from 2 to 10%, and its formation permeability is between 1 microdarcy and 0.1 millidarcy. These are both factors that dominate the fluid movement and behavior between pore spaces in shale. These low values have historically contributed to the complexity and inability to produce shale reservoirs commercially. Thermal recoveries such as hot water flooding may prevent viscous fingering by reducing oil viscosity drastically, and thus reducing the mobility ratio. Yet, problems often arise because of the cost of such operations and the necessary infrastructure that comes along with such projects. Steam efficiency reduces with reservoir depth, and the process as a whole is not very environmentally friendly. The top right image of chemical injection is similar to an inverted 5-spot flood pattern. Chemical injection is performed with polymer addition to increase the viscosity of the water that is being injected into the formation. Because the viscosity of oil is so high, increasing the water viscosity with polymer injection helps to decrease the flooding system's mobility ratio. Towards the end of a polymer flood, the relative permeability to water is decreased, which further aids in obtaining a more favorable mobility ratio. However, having a high water and oil viscosity may reduce production rates. The bottom image depicts how gas injection can be performed with various substances such as nitrogen, carbon dioxide, and hydrocarbon gases like methane and ethane. In regards again to the mobility ratio of a system, the relative permeability of gas is so high that viscous fingering frequently occurs, causing high instability within the flooding system. This, coupled with the need for enough CO2 oil contact time, is the reason why cyclic CO2 stimulation is often used. The gas injection process can either be miscible or immiscible depending on how a reservoir's pressure compares to its minimum miscibility pressure, which is the point at which gas and oil become singular phase. If the reservoir's pressure is above the MMP, miscible CO2 flooding takes place. Our project focuses on miscible CO2 flooding because it is proven to show a more efficient recovery factor in comparison to immiscible flooding in conventional reservoirs. However, CO2 EOR remains unproven as an efficient unconventional recovery method. There are two classes of mechanisms that can be considered in regards to carbon dioxide EOR: the trapping and the mobilization of crude oil, which is what we will be focusing on. The trapping mechanism deals with CO2 geological storage in places like deep saline aquifers or abundant reservoirs suitable for geologic storage. The factors displayed are a result of CO2 miscibility with crude oil in a shale reservoir. From an EOR perspective, only low-density and highly compressible fluids like CO2 can invade the extremely small pore spaces and throats that are characteristic of shale to mobilize the trapped resident fluids. In terms of oil mobilization, interfacial tension is the force resulting from imbalanced cohesion at the interfaces between brine and oil, two immiscible fluids. As carbon dioxide is injected into the reservoir, IFT between the oil and the brine reduces. At the minimum miscibility pressure, IFT becomes zero, which favors oil recovery as oil and brine flow as a singular phase. As a result of these reservoir changes via CO2 injection, more favorable conditions are present in the formation, allowing the mobilization and production of the reservoir hydrocarbons in much larger quantities. These mechanisms that have been discovered for CO2 in conventional reservoirs are also expected to be suitable in shale because Such mechanisms are largely dependent on reservoirs' fluids and less on rock characteristics.
We were fortunate enough to receive real data from a field in Mexico from Pemex. Some of the acquired data we received from the reservoir was the original oil in place, porosity, permeability, reservoir thickness, oil saturation, water saturation, skin factor, and the information goes on. We input some of the PVT data into the simulation software, which ended up giving us a range of values, which is very useful so we could run our simulation. If you look at our relative permeability curves that was deduced from the model from Pemex, you can see that the crossover point is greater than 50% water saturation, which actually means our reservoir is water wet. And since it's water wet, it's going to be able to give us a better sweep efficiency. Next. So since the reservoir info we received from Pemex was for a sandstone reservoir, we actually had to deduce some characteristics for our own model to simulate a shale reservoir. This mostly depended on the porosity and permeability. So we went with a porosity ranging from 10% to 5%, and we decreased this with depth due to compaction effects. We went with a permeability of 0.01 millidarcy in the horizontal directions, and a permeability even lower of 0.001 millidarcy in the vertical direction to simulate shale in the best way. We also had to use the material balance equation to back calculate our reservoir model size. Since the porosity was so much lower, the original oil in place needed to be the same. So our reservoir model is actually significantly larger than the reservoir size from actually acquired from Pemex.
So after we finalized our model in CMG, we began to put our injectors and producers into the model in the desired flood patterns. And as you can see from these aerial shots, we started with the direct line drive by putting in 9 injectors and 6 producers, each equidistant from one another in the X and Y.
Once the direct line drive model had been developed, we then moved on to our staggered line drive model, which is the same amount of injecting wells, but we removed one producer from each line and then shifted them over so that they were staggering the injecting wells. Once the staggered line drive model had been put in place, we also used the same model for Huff and Puff, but for this model, we would shut in the producing wells for 1 month at a time and then open and produce those wells for 3 months while constantly injecting gas into our model.
For our horizontal wells, we went with 6 horizontal injectors as well as 4 vertical producers. For the horizontal wells, we went down to the 4th layer before the wells went horizontally towards the center of the model. The model geometry isn't exactly perfect right now, but we're working with other patterns in the future.
And our last model that we developed was a non-spot flood. In this model, we surrounded the reservoir with injector wells around the boundary, and then we split the model into quadrants. So we placed even more injectors in the center of the well vertically and horizontally, and then we placed 4 producing wells inside each one of these quadrants. So total, in each quadrant, you will have 8 injecting wells and 1 producing well on the center of the model. So here we've recorded our pressure regime for both of the direct line drive and the staggered line drive. Like we said in the slide before, the only difference with these is in the staggered line drive, the producing wells have been shifted over. For these, it's worth noting that we have perforated our reservoir for all injecting and producing wells in all 6 layers of our model. We decided to record the pressure regime because we felt that this showed a very effective way of how our fluid was flowing through the reservoir and our flood patterns. And out of the 2 of these, the direct line drive was the more effective flood pattern.
For the Huff and Puff injection on the left, we closed in for a month, injecting CO2 before opening again for production for 3 months. We continued this process for the entire 10-year life of the well. For the 9-spot pattern on the right, we can see a more uniform pressure regime. Both of these patterns produce the least effective sweep efficiency and recovery factors.
For our horizontal wells, the pressure profile we went with was on the 4th layer. This was the location of the horizontal wells. It makes it easier to see the sweep. The permeability was the highest in the X and Y direction, which is why you see a better sweep efficiency for our horizontal wells.
So after all the models were ran, we were able to gather our production data and compare all of them from the 5 different floods that we ran. As depicted in the blue solid line, the staggered line drive injected at a rate of just under 460,000 standard cubic feet a day, but only recovered less than 1% of the initial oil in place. This was the third largest producer of our 5 model floods, and the recovery factor, like we said, was just under 1%.
And shown by the pink line on the graph, the direct line had a relatively good cumulative production compared to the others. It had the second best recovery factor with an injection rate just under 450,000 cubic feet per day.
The next model, which is depicted by the red dash line, is the 9-spot model. Due to the proximity of the injecting wells to one another, we were only limited by CMG to inject 2,000 standard cubic feet per day per injecting well, which is why the injection rate is only a tenth of that of the other 4 flood patterns. Even with this low injection amount, we still saw production of over 34,000 barrels, but this is still just a small recovery factor of less than 1%.
The huff and puff was denoted by the dash green line. The dash blue line. It's kind of hard to see behind the other ones, but it's in there. The production for the huff and puff was one of the lower sides. We assume this is because the wells were shut in for an extended period of time. The recovery factor for this was actually pretty low, less than 1%. For the horizontal wells, the production was the greatest at a little over 82,000 barrels. The recovery factor was a little over 1.4%. And as you see on the trend, it is actually a little exponential. The oils produced per day were increasing as the time went on, which is good because if we went on for longer than 10 years, our production would have been exponentially higher. All the models had a pretty similar initial production rates, as you can see, like before 4 years. But after 4 years and sort of the later life of each model, the production profiles all differed greatly.
So as you can see here, only one of our wells recovered over 1%. So we still do have some work to go in trying to increase the recovery factors of all of our wells, which is how we're going to proceed with our models.
Once the technical aspect of our project is over, we're going to move on to our economics. It's going to be great if we can recover oil from EOR, but a project will not be moved forward if you can't do it in an economical manner. Some things we're taking into account are capital costs, operating costs, prices of gas injection, and other assumptions such as inflation rates and tax rates.
So assuming a 10-year production life of our reservoir, the profit for the first 5 years can be equated by production revenue versus expenses such as capital, operational, taxes, and royalties. It is our goal to achieve break-even for capital expenditure after 5 years of CO2 EOR production. With this prediction, the profit equation would then change to revenue less operational expenses and tax.
So as of now, our recovery values are a little lower than expected. As we move forward, we are trying to maximize production by optimizing our well pattern geometry, our injection cycle and rates, and our injected fluid composition. Our realistic and extensive simulations will aid in determining the potential that lies in shale production without fracturing. Even if we can attain recovery rates of at least 7 to 10%, fracturing could then be implemented to further enhance production percentage. This would obtain a profitability baseline and show the potential of shale production with CO2 EOR.
Once we have performed our economic analysis, we will be able to determine whether or not the CO2 EOR project is technically and economically feasible and possible to be used in the real world.